Science Olympiad, Class 9. Sound.
Introduction. Sound, like heat and light, is a form of energy. Sound travels in waves. Waves are vibrations that occur in a material as sound passes through it. When we listen to someone speak, our ears detect sound waves in the air around us, caused by the person's vibrating vocal cords. Sound is produced by the compression and rarefaction of matter. Sound waves are mechanical waves. They move through air because the vibrating source produces regular variations in air pressure. This lesson features the kinds of wave motions, free and forced vibrations, and resonances. This chapter demonstrates the kind of waves, working of a sonometer, Doppler effect, and its applications. Stationary waves. A stationary wave is formed when two identical progressive waves traveling in opposite directions overlap, are superimposed on one another. Stationary waves in a string can be demonstrated by fixing one end of the string to the prong of a tuning fork and passing the other end over a pulley. The string is kept taut by a weight attached to the free end. When the fork is set in vibration, a progressive wave travels along the string to the other end and is reflected back. If the fork is kept in vibration, the incident and reflected waves combine to form a stationary or standing wave, and the string vibrates in a series of equal segments. Franz Melde of Germany performed this experiment in the middle of the 19th century. The points marked N are called nodes, and here the string remains at rest. Midway between the nodes, the string vibrates with maximum amplitude. These points A of maximum amplitude are called antinodes. The distance between two adjacent nodes or two adjacent antinodes is half a wavelength, lambda by 2. The distance between a node and adjacent antinodes is a quarter wavelength, lambda by 4. The sonometer. The sonometer consists of a hollow sound box which is about a meter long. A thin wire is tied to a hook at one end of the sound box. The other end passes over a light smooth pulley and carries a load W. A and B are two movable bridges so that the length of the vibrating segment AB can be adjusted. The wire is set into vibration by plucking it between A and B. Vibration of air columns. When an air column produces sound, a longitudinal stationary wave is set up in it. When the air column in pipes vibrate, a node is formed at the closed end and an antinode is formed at the open end. Closed organ pipe. Consider a cylindrical pipe open at one end and closed at the other. When the air column in the pipe is set in vibration, there is a node formed at the closed end and antinode at the open end. The frequency corresponding this node is called the fundamental frequency. The frequency is obtained as shown above. The air column can also vibrate at higher frequencies called harmonics or overtones. Frequency of first overtone, third harmonic, is obtained as shown on the screen. Open organ pipe. Consider a cylindrical pipe open at both ends. When the air column in the pipe is set in vibration, antinodes are formed at both ends. Fundamental frequency is derived as follows. Hence, the fundamental frequency of an open organ pipe is double that of a closed organ pipe of the same length as shown. Frequency of first overtone, second harmonic, Doppler effect. Whenever a fast-moving ambulance or fire engine or the pilot car of a VIP or a train passes you with its horn or siren or whistle blowing, its pitch seems to change. The sound you hear is higher as the vehicle approaches you and lower as it moves away from you. This is an example of Doppler effect, named after the Austrian physicist Christian Doppler, who discovered it. Doppler effect is the apparent change in frequency due to the relative motion between the source and the observer. Applications of Doppler effect. To help the traffic police detect the speed of vehicles. When an electromagnetic wave of constant frequency emitted by a source attached to a police van is reflected from a moving car, there is a shift in the frequency of the reflected wave. The shift in frequency enables the police to determine whether the car is traveling at the permissible speed limit or not. Bats sense the velocity of objects around them by the Doppler frequency shift of the ultrasonic waves produced by them. They can estimate the distance and the size of objects as well. Doppler effect is used to determine the velocity of a submarine relative to an observer in a ship. Doppler effect is used in the medical industry also for diagnosis. Example: an ambulance speeds down a highway at a speed of 35 meters per second. Its siren emitting a sound of frequency 400 Hz. What frequency by a passenger in a car traveling at 25 meters per second in the opposite direction as the car A approaches, B moves from the ambulance. Solution: let us assume the speed of sound V as 330 ms to the power of -1. Vs is equal to 35 ms to the power of -1. Vo is equal to 25 ms to the power of -1. N is equal to 400 Hz. When the car approaches the ambulance, N is equal to N into V plus Vo by V minus Vs is equal to 400 into 330 plus 25 by 330 minus 35 is equal to 461 Hz. When the car moves away from the ambulance, N is equal to N into V minus Vo by V plus Vs is equal to 400 into 330 minus 25 by 330 plus 35 is equal to 334 Hz. Progressive waves proceed in the medium without being reflected back at any point in their path. The two types of progressive waves are longitudinal and transverse waves. In the case of longitudinal wave, the direction of vibration of the particles of the medium is parallel to the direction of propagation of the wave as shown in the figure. Whereas, in the case of transverse wave, the direction of vibration of the particles of the medium is perpendicular to the direction of the propagation of the wave. Characteristics of sound waves. The characteristics of sound waves are shown in the table. Beats. When two sound waves of slightly different frequencies traveling in the same direction interfere, they combine to give waves whose resultant intensity changes between a minimum formation of echo. In the figure, PQ is the reflecting surface that is placed in the path of the sound. Let the source and the listener be at O. When source emits sound, OB is the path of the incident sound wave and BO is the path of the reflected sound wave. If reflecting surface PQ is at a distance D from O and if T is the time of echo, we can write as above. If the velocity of sound is taken as 330 meters per second in air, this sound travels a distance equal to v into t is equal to 330 into zero point 0.1 is equal to 33 meters in 0.1 second. That is, 2d is equal to 33 m and d is equal to 33 by 2 is equal to 16.5 meters. Hence, reflecting surface must be at a distance of 16.5 meters from the observer. Application of echoes. The applications of echoes are shown in the table. Reverberation. When a man standing in an open space produces a sound, it is heard by a listener after a time interval. T is equal to x by v, where x is the distance between the source of sound and listener and v is the velocity of sound in air. If the sound is absorbed in the medium before reaching the listener, it cannot be heard. Let S represent the source of sound, say a loudspeaker, and O represent the position of the observer in the closed room. Then the observer receives the direct sound along the path SO and also hears the same sound along the path SAO after one reflection at A, along the path SBCO after two reflections at B and C, and along the path SEFGO after three reflections. Fundamentals of building acoustics. The branch of physics dealing with production and controlling the factor relating to the design and construction of cinema theaters, auditoria, concert halls, etc., so that the speech, music, and songs are clearly reproduced to give a pleasing effect to the audience is called acoustics of building. The subject that deals with the construction of good auditoria is called architectural acoustics. The sound produced in a closed room at a point undergoes multiple reflections at various surfaces present within the room. Thus, there exists reverberation of sound. Hence, in the construction of large rooms, some conditions such as the ones shown above are to be fulfilled. Building acoustics. Conditions are shown in the table.
Wave pulse. A disturbance is called a wave pulse if it is confined in a small part of the medium at any given time. Periodic wave. A wave is called a periodic wave if the particles of the medium carrying the wave repeat their motion after fixed intervals of time. At any given time, the state of each particle in a periodic wave is the same as that of another at a fixed separation. Crest and troughs. A portion of the medium where the wave quantity has a value larger than its normal value is called a crest. A portion where it has a value smaller than the normal value is called a trough. Mathematical equations involving wavelength, time, period, frequency and amplitude. F is equal to 1 by t. Lambda is equal to Vt. V is equal to F lambda, where F is the frequency, t is the time period, lambda is the wavelength, and v is the velocity of the wave. Reflection of sound. When sound is reflected, the direction in which the sound is incident and reflected make equal angles with the normal to the reflecting surface, and all the three lie in the same plane. Reflection of sound has many applications such as stethoscope, horns, megaphones, sonar, ultrasonography, etc. Refraction of sound. During night, distant sounds such as that of traffic are often louder than during the day due to refraction of sound. Diffraction and interference. The wavelengths of audible range varies from 1.5 cm to 15 meters. If obstacles of similar dimensions are in the path of sound, diffraction of sound takes place.